Hello, fellow problem solvers. So today we're going to be doing a problem from the United States Team Selection Test 2015 problem number 1. This is a geometry problem I really like because it's, just look at the problem statement. Prove either this or this is true. And it's completely symmetric. And I invite you to pause and try it out for a minimum of half an hour, ideally an hour and a half to 2, not more than 3.5, actually not more than 4.5 hours because this is the first problem at the TST. You wouldn't have more than that much time, and you might get better at geometry trying to solve it for that amount of time. If you'd like to go along with us, give this a go for the next 10 minutes, put your first ideas out on paper, and now let's begin. So we have in geometry, what you can do is solve the problem forwards or backwards. And when you have a lot of things, you try to take them one at a time. So first, I have the incircle and the triangle. And usually when you're drawing this, you first want to draw the incircle and then draw the triangle around it, just because that is, generally speaking, easier usually. And it's non-scale. It's non-isosceles-ish. And what I think matters here, because everything's symmetric around A, or B and C are symmetric in this problem, like how everything's defined, I think the important part is that A, B, and AC aren't equal. Like that's this whole condition, because anything else shouldn't really be affected, but potentially it is. Potentially it is, but doesn't really seem like it to me. Okay, so now we have these things. And I'll pay attention to how the points M, P, and Q are just defined. Right, you're given P, that's on this line AI, such that MP is equal to MD, okay? And I guess if we draw M to be somewhere around here, that's going to give us a P over here. And then Q is also just like popped into our problem, just pops in. It can pop in near the end, wherever we want it to pop, but it's also given to us as an afterthought. Oh, and there's this point Q. So what that tells me is that we can analyze those P and Q separately because they're only combined in our problem condition. And what's interesting also is note that the way Q is defined, Q is like going to be somewhere here, is that PQE or PQF is 19. Now here, it seems like PQE is 19. The interesting part about that is that why do we not have, where do we lose the symmetry with B and C? And pause for 2 minutes, ask yourself, where do we lose that? And the answer is, well, mind you, the only place where we don't have full symmetry is not with Q, but it's with P. Right, it says point inside the triangle such that MD is NP. So if we took a point outside, and there's another point outside here, call this point R, we'd probably have RQF. It looks like that is 90. So that's probably why P is like this. Now, I invite you to pause for the next 10 minutes and try to figure out everything you can about point Q, because it's really about trying to connect these 2 points, P and Q. So let's start off with Q. Pause for 10 minutes and do that. Let me clear up the board here. Okay, so now we've cleared the board up and we have this. Now we want to find stuff out for Q. How do we do that? What is sort of like a first sort of step to try to connect Q to everything we have? And the answer is, well, you want to understand, and it's a general sort of meta heuristic in geometry, you want to understand how this point is constructed. Like how would you get to a point Q, right? So let's see, we have that Q, AQD is going to be 90. What does that mean? How would you make this point, right? You could say, oh, I'd take the midpoint of AD, and then I'd draw a circle with center there. Sure, potentially, that could be a way. There's another way that might be quicker, so to speak. Just doing intersections. Pause for 2 minutes and think about that. And the answer is, well, I'm going to have AQD is 90. So if I intersect here, AQ, I'm going to get that if this point is, say, T, I'll get that TD is the diameter of the incircle. In other words, TID will be collinear. So how can I construct Q? Well, I intersect DI with the circumcircle again at a point called this T. And then I intersect AT again with the incircle. And I get the point Q. So this is how I can construct point Q. Now, given this construction, is there anything else I can find out about Q? Like, what type of AQ? Is this sort of a well-known line? Like, how would you connect this Q to, like, D, E, F are well known. ABC, incircle elements of a triangle. How does Q relate? Or AQ, how does AQ relate? How do BQ and CQ relate to that? Because we're going to need to relate it to AI at the very minimum. And let's think about this. So we can go at this problem for many different directions. One way is to go backwards now and say, okay, wait a second. I'm going to have PQE is 90. Let me draw AI. And for PQE, I have this is 90. So I'll have P will need to be a point here such that this angle is equal to this angle. And what else is this going to equal? Now that's one way of going about it, and you see, okay, this is going to equal EDT as well. Is there a connection between P, E, and T? We don't know. I'm always to say, okay, what does this, angle condition give me? I have this angle is then also equal to this angle over here. And from there, do I have anything? I have a power of point. This squared is this times this. Do I have AI times AP? Is that equal to anything remotely interesting? Are these potentially concyclic? And it seems difficult to think that they are, because if these would be concyclic, maybe actually, who knows, maybe they are concyclic. I'm actually legitimately not sure whether or not they're concyclic. But there's a lot of questions we can have here about Q, trying to solve the problem backwards. And then the other thing is, these are the two ways to solve geometry, forwards or backwards, is to say, okay, what do we know about, say, AQ, ATQ? Is this a well-known line? And let's see what we have from the angles. Like, do we know this angle? Or do we know anything about this angle? I'm always say, okay, let me see what I have trigonometrically. This is x, this is alpha minus x. And I can get I can get this intersection here. I'll get what this over this is by doing sine x over sine of alpha minus x. And then what I'm going to have? I'm going to have sine x over sine gamma. And everything's going to cancel out. So I'm going to have times sine of beta over sine of gamma is going to give me, call this point ATQS, is going to give me CS over BS. And now can we maybe connect this X to the elements of this incircle? And it seems like we can, because this is like, we can look everything here as DEF is our main triangle. This is where the tangents meet, and this is the point where we have such that DT is the diameter. And then we can probably calculate these angles, like get the sines here, by forcing it on these two triangles. And in fact, we do have these angles, like for example, also wait a second, this angle X, is that well known? Because that's equal to this angle over here. So we can also just do some angle chasing first. And here's where I invite you actually to pause for the next 10 to 15 minutes and do some angle chasing. figure out the problem on your own. And here's what the next thing. So the angle chasing goes, and we get all these angles. We get beta, alpha, alpha. We get these are gamma half, beta half, and we get now from sine of x when we do trigonometry on these two triangles. And we get that sine of x, or sine of alpha minus x, is sine of gamma half, or sine of beta half, times TE over TF. Now T over TF, we can do the sine again on that triangle, and we get that this thing, sine x of sine of alpha minus x, is equal to sine of gamma half, or sine of beta half, squared. So let's put this in here, and what we get, this is equal to, we're going to have, so sine of gamma half, or sine of beta half, squared, and then this thing right here, we can transform this as sine of beta half, cosine of beta half, sine of gamma half, cosine of gamma half, is equal to CS over BS. And then this turns into, so one sine cancels out on every single side, and we're left with tangents of gamma half over tangents of beta half. Now, can we connect this to the elements of the triangle? Pause for 5 minutes, think about that, and the answer is yes, we can. Well, we can do BID and CID. We can have tangents here is going to equal ID over DC, ID over DC, and then here we're going to have ID over DB. In other words, this is equal to DB over DC. So we have CS over BS, this over this is the same as this over this. Add 1 to both sides and you get that CS is equal to BD. And this is also a lemma, somewhat well known, and it's good to keep these lemmas in mind. But this is one way of motivating that. Another way of motivating that is to say, okay, wait a second, if I draw a line parallel through C, parallel to BC, intersected with the sides of AB and AC, so that'd be B1 and C1, what will I have? I'll have two similar triangles, and I'll have T, like the incircle here is the excircle of AB1C1, and that means T and S will, in the similarity, T and S map to the same point, and then we can have that the angle TAC1 is SAC, and given AC1C are collinear, we can get ATS are collinear. So those are like two different ways of getting to the same thing. And now we have sort of something about Q that's interesting. We have this is a 90-degree angle, and we also have that CS is BD. Now pause for 5 minutes and think about what happens when you add M. And the answer is, well, when you add M, because MB is MC, this is this, so MD is MS. And given this is a 90-degree angle, well then so is MQ is MD is MS. So this point P that we're going to have actually lies on the circumcircle around, in the circumcircle with the circle with center M and radius MD, right? And MQ is then also what to the incircle? It's a tangent. So we have a lot of things now that we know about Q, and we've connected P and Q somehow. Like we've shown that MQ, MP, MD are equidistant. So Q and P now have some more connection, are more grounded. And now let's think. So we know that MQ is MP is MS. And now we need to show that this angle is equal to this angle to show that we have PQE is 90, because this one's 90. But this angle right here, we know this angle from angle chasing that it is equal to gamma half. So that means we need to show that this angle is gamma half. In other words, because this is the center of the circle around dpq, this angle would then be gamma. In other words, we'd have PM is parallel to AC. That means, because M is the midpoint, it means that P would lie on the midline of the triangle, of the B midline of the triangle ABC. So we'd have the angle condition and a parallel condition. Now we could go ahead and say we define P like this, we know it's on the circle, and then we try to prove through some computation that PM is actually parallel to AC, right? We need to get, oh, we actually need to get, it seems potentially plausible. The difficulty is getting to this thing right here. If the intersection here is, say, X, to get what XP is equal to. That is the only major difficult thing here. But let's see, and this is a moment where I invite you to pause for the next 15 minutes and try to push the problem further. Because here's, let's pause and think for a second. What gives us more things? If P defined like this, just an intersection of AI and this, on this, it being on this circle, for which we know not super duper much about. Like, we know these are tangents, but do we have the angle with dq? Well, we don't really have it precisely right now, at least I don't think we do. So it seems, what do I have? I have this angle. If this is x, then this angle here is x. I have this here is 2 times x. Well, now this here is x because MD is MQ, IQ is ID. So I have these angles. Does this connect to P in any way, shape, or form? It seems difficult. Maybe there is. If you've paused and figured it out, please let me know in the comments below. But for me, the thing is, wait a second, let me try to see what happens if I redefine P. If I get, instead of a condition of length, if I get a condition of angles and a parallel line. So let's now do that. And what we get when we draw a diagram is we have P prime here. And I don't know for you, but for the diagram I have just drawn, I get that this P prime, it looks awfully like it's on DE as well. And in a problem condition, my question is, wait a second, I have EDI is equal to gamma half. I want to get that this is gamma. In other words, that the angle here is gamma half. ID is tangent, because this is a 90-degree angle, to the circle. So it makes sense that D, P, and E are collinear. And now if I try to see what is maybe, that might be a better definition of P. Maybe if I define P as this intersection of DE and AI, I can get maybe something else that connects P prime to the midpoint. And think about it, wait a second, I would get that this angle is alpha half because this is the midpoint, right? I just get that from angle chasing because this is parallel to this, I get this is alpha half. Now from the fact this is the midpoint, I get that AN is NP prime, but this is NB. So this angle right here, AP prime B, is 90. I don't need to redefine it. I would probably get the same thing doing this. And the answer is I would. And the thing is, that means that these 4 points are then concyclic. And if I'm trying to prove that E, P prime D are collinear, I have P prime DI is going to be equal to this angle. So I have this as 90. And I should probably get by angle chasing that one of these angles is gamma. Now the only question is, how can we get that? And I invite you to pause for 10 minutes, either working with this picture or this picture, to try to prove that, I try to prove either here that E, P prime D are collinear, or here, realistically, what you need to prove is that P prime is on the circle around B, D, I, F. Okay? So pause for 5 minutes, 10 minutes, maybe 15. Think about that. Try to prove it. And the way I do it is ask yourself, what angle do I have here with P prime? And the answer is, well, the way I've defined it, I only have this angle P prime I, F. And I have this angle is going to equal 90 degrees. And then this is 90 minus alpha half, so it's going to be 90 plus alpha half. Which means that P prime BF is going to equal what? It's going to be 90 minus alpha half, or beta half plus gamma half. And now, given this is already beta, that means this has to be beta half, this is gamma half, and that solves that these 4 points are collinear, because then I have this angle is gamma, P prime DI is gamma half, and E DI is also gamma half. Why? Well, these are all concyclic. And then this really just finishes up the problem. So how would we write this down? Well, we would say, we know this thing for Q, and we'd say, well, it's enough to prove that the angle PQD is gamma half, or it's enough to prove that PMD is gamma, which means it's enough to prove that PM is parallel to AC. And then from there, we go and say, let's take P prime to be this. Actually, the other way to do it. I'm going to redefine P prime to be the intersection of AI and DE. And now what I say this is alpha half. We know this angle is alpha half plus beta half. So this is beta half, which means that given the sum of this angle plus this angle is 180, that means these 4 points are concyclic. And now, given these 4 are concyclic, it means I P double prime P is equal to I D B, which is equal to 90. So if I take the midpoint here, and I connect it, take this midpoint N, and I connect it, I get this is alpha half, because this is 90, hypotenuse, the midpoint of the hypotenuse, this is alpha half 2, which means this is alpha. This gives P prime N what? Well, it gives that P prime N is parallel to AC, so P prime N passes through the midpoint M. And now what do we have? We have this angle here as gamma. We know that this angle, EDM, is equal to alpha half plus beta half, which then implies that this is alpha half plus beta half. So MP prime is MD, given this is the unique point inside the triangle such that MD prime is MP prime. That means P double prime and P are the same point, and that finishes up our problem. And the reason I really like this problem is, I mean, it's an application of two really lemmas in some way, shape, or form, but it's disguised very well, in my opinion. And I guess what else I really like is just how it said or, PQE or PQF. And with that or, you're trying to think how, like, where's the asymmetry happening? And then you realize, okay, the asymmetry is happening because it's inside or outside. If I take the outside point, I get symmetry. I can see that from my picture. And then you're trying to see, okay, wait, P and Q are really just added there together, but separately, really. They don't have anything to do with each other except in the final analysis, in the final problem statement. And then you say, okay, so let me analyze Q. With Q, you get that this is not only 90, but that AQ passed through where the X circle touches BC. And from there you get this connection. And you realize, okay, wait a second, solving the problem backwards, I need this. You know, that application is just seems to be step by step, like very a trained problem. Not too many big ideas, but I just think it's aesthetically pleasing to see a problem statement have an or in geometry. Now this finishes up our problem, and as always, Thanks for problem solving.